Hello, welcome to week two's IMechE challenge repeatable vehicle presentation presented by Team AB17. So due to the pandemic, our challenge goal has changed. Now the goal is for the vehicle to do a total track of 3 meters as far as possible whilst using the least amount of energy.
So there has been three changes made to the design. The spring system has been improved to have a stiffness of 110 newtons per meter to help with the cushioning during the impact with the wall. The gearing system changed to have a gear ratio of 1:36 to make the device faster and to decrease stress on the motor shaft. We also added support to help with the structure of the device.
This is our final CAD model. All the elements rendered in white, except for the gears, will be 3D printed. The main frame will be made out of 3mm birch plywood, and the gearbox walls, as well as front support, will be made 10mm thick and secured in place using a cyanoacrylate adhesive.
The cost of all the materials met the budget at £30. Some quantities are displayed as decimals or fractions. This is because the item comes in a pack, and the number represents the percentage of the pack which we require. The pricing for the 3D parts was calculated by finding the price of 3D printing filaments per gram, which we found to be 2p.
We did some iterative calculations to estimate the total energy we might consume. The net force to accelerate here is equal to driving force R minus the drag and rolling resistance forces. Here you can see the formulas used for losses. We initially assumed a coefficient of rolling resistance of 0.1 and a drag coefficient of approximately 1 to provide a sensible starting point. Energy is equal to driving force multiplied by distance, and we used the formulas above iteratively using a spreadsheet to calculate energy at each time step and found the total. We did this to make an order of magnitude estimate and make a comparison and sanity check the simulation output and see what the assumptions may have been used.
So we initially ran 3 simulations for different spring rates to set benchmarks on how we want or not want our vehicle to decelerate at the wall by comparing the gradients between 3 and 4 seconds for each of the graphs above. We eventually settled down on a spring of length 53mm, a diameter of 5.4mm, and a stiffness of 110 Newton per meter.
So as you can see, this is the final data that we use for the simulation. Total mass comes out to be 0.56 kilograms, and all the dimensions data that we took is from the CAD model. The gear ratio has been changed from 108 to right now 36. The spring stiffness is 110 Newton per meter.
And this is our final simulation.
The velocity time graph for the simulation is shown here. For the first 2 seconds, the program starts up, but the simulation doesn't begin. As you can see, the velocity increases rapidly to an almost constant value. This is because the distance is not big enough for it to reach the constant value. The vehicle then hits the wall and decelerates rapidly, after which it accelerates in the opposite direction, back to the original position. The total time taken for this is 5.34 seconds, and the maximum speed reached is 1.12 meters per second.
The graph shows the simulation energy output is increasing and different to our calculations, so we realized this was cumulative and in terms of energy per time step. Therefore, we multiplied the last value in the energy users output column by the time step of 0.005 seconds to give us an energy of around 2.69 joules, which is very close to our iterative estimate calculations, which we decided was the best compromise for low energy and to meet the competition requirements.